We have our first principles formula, which allows us to differentiate, but let's face it, that's a pain in the neck, having to do that every single time. But what it does allow us to do is create formulas, which will then make life easier for ourselves. Let's start at the very most basic one. Yes, we know what the answer is, but let's prove it using our first principles formula. So y is equal to some constant number, then the function is a constant, but then that also means function x plus h is a constant as well. So when we substitute it into our first principle formula, we do get 0 over h, which is of course 0. So the limit is also 0. So anytime we want to differentiate a constant, we get 0. So let's build it up and go, well, what about when it was some multiple of x? And again, we know that should end up being k because it's the slope of the line. But let's prove it. Function x is kx. Function x plus h would be kx plus h. Subbing that into our formula. And the h's now cancel and we get k. So it confirms what we already know. Our problem then came with what happens when we go higher up with those powers. So x to any power of n. Now in order to do this, I just want to remind you of a few things. We have a formula for the difference of two squares, a minus b, a plus b. We have a formula for the difference of two cubes. And in fact, we could generalize it and keep going, and we get this idea that a to the power of n minus b to the power of n will always be a minus b. And then in the second set of parentheses, the power of a will go down by 1, the power of b will go up by 1. The two powers always add up to be n minus 1. It's that last line that I'm going to use. Function x is x to the power of n. Function x plus h is x plus h to the power of n. So into our first principles formula, I now have this, x plus h to the power of n minus x to the power of n, and that's where I'm going to use this factorization. In the first parentheses, I get x plus h minus x. And then in the second one, the powers of x plus h are going down by 1. The powers of x are going up by 1. But of course that first parentheses, x plus h minus x, is just h. And that will cancel with the h in the bottom of the fraction. And I'm left with this series. But if I substitute h equals 0 into all this, then I get the first one becomes x to the power of n minus 1. The second one becomes x to the power of n minus 2 times x, which is x to the power of n minus 1. And so on, and so on, and so on. So every one of those terms is x to the power of n minus 1. I guess the question is, how many of those terms do we have? Well, if we go back to our pattern, when it was a squared minus b squared, there were 2 terms in the second one. When it was a cubed minus b cubed, there were 3 terms. A to the power of 4 minus b to the power of 4, there are 4 terms. Now, logically, a to the power of n minus b to the power of n, there must be n terms in the second one. So we have n lots of x to the n minus 1, and we now have a nice, neat formula that allows us to differentiate any polynomial that we like. Y equals 7, we know that's a constant. We can now just say, well, the y dx is 0. We don't have to use first principles. Y equals 37x, well, the derivative is 37. Again, we don't have to use first principles. But now, x to the power of 10, we simply bring down that power and then lower the power. 10, x to the power of 9. If we have more than one term, we just do each piece individually. So 3x squared, well, when I bring that power down, 3 times 2 becomes 6. X to the power of 1, the 6x becomes 6, and of course the 2 becomes 0. So we have 6x plus 6. 2x plus 1 squared, we will see a rule later on that would help us with this. Mind you, I don't know if I'd use the rule for this particular one anyway. But at this stage, we'll expand it out. So 4x squared plus 4x plus 1, differentiate each individual bit, and we get 8x plus 4. If function x is x cubed minus 3, find f dash 2. Now make sure you read the question carefully. It's so easy to make a mistake here and think it's just asking me to substitute 2 into the function. No, it's not. It's asking you to substitute 2 into the gradient function. First thing we have to do, of course, is find the gradient function. Function x is x cubed minus 3, then the gradient function is 3x squared. So f dash 2 would then be 3 times 2 squared. It gives me 12. Find the equation of the tangent to the curve. Remember, this was one of the original problems we were posing while we started looking at this whole thing of calculus. Y equals 5x cubed minus 6x squared plus 2. Differentiate that. Let's find that gradient function. Remember, that is the function that allows us to find the gradient. Now we will substitute in the value we're investigating when x equals 1, and we get 3. So I know the slope I want is 3. Point slope formula, and there it is. I've put it in general form, however you prefer to do it. Find the points on the curve where the tangents are horizontal. So what are they saying to me? The tangents are horizontal. There's the function. There's its derivative, 3x squared minus 12. Well, I know that when the tangents are horizontal, then that gradient function must equal 0, because horizontal lines have a slope of 0. In other words, this is what I have to solve. It's going to happen at 2 different x values, plus or minus 2. They've said the points. Again, that brings me up to the next thing to be careful with. Make sure you substitute back into the function, not the gradient function, because of course if you substitute back into the gradient function, you'll get 0. That's what we just solved. Putting it into the actual function itself, we have minus 2, 16, and 2, minus 16. Now a word about setting out of your solution. Explain why you're making it equal to 0 and things like that. Don't just go, oh, dy dx equals this equals 0, here's my answer. Remember, you're presenting a solution to someone. They need to interpret what you're doing. So explain to them what you are doing. Now there's this thing called a normal. A normal is a line perpendicular to the tangent at the point of contact. Here's a random curve, there's our tangent. The normal at that point is the line that's perpendicular to it. So if we get a question like this, then again we're going to say, well, I need a point and a slope. I have a point, what's the slope? Well, I can work out the slope of the tangent. Let's do that. So y is 4x squared minus 3x plus 2. There's our gradient function. The slope of the tangent is 21. Therefore, the slope I want is the negative inverse of that. The negative 1 on 21. Put that into our point slope formula. And they're not nice numbers, but they are what they are. X plus 21y minus 612 is equal to 0. A note about the setting out. I just said, don't be lazy, but also do it correctly. What do I mean by correctly? You're actually solving an equation. Okay, you are solving an equation. It's still this idea of what you do on one side, you do on the other side as well. Because you know this thing is equal, I've got to keep it equal. So when I have this, what I am actually doing is this. If I have y equals x squared plus 2x, I'm saying, well, I want to differentiate both sides of this equation with respect to x. That's what I'm actually doing. So what I'm really doing is saying on the left-hand side, I want to differentiate y with respect to x. And on the right-hand side, I want to differentiate x squared plus 2x with respect to x. That ends up with this result, the y dx equals 2x plus 2. You'll notice this big gap, because that's what I'm really doing. You see, I can't differentiate y with respect to x, but I can differentiate it with respect to y. But I can't change the fraction, if you like, because derivatives are rates, rates are fractions. So to balance it out, I multiply it by dy dx. Now differentiate y with respect to y, you get 1. So dy dx is 2x plus 2. That's what you're actually doing. Now, of course, you don't write all those middle steps down, but you certainly write the first line down and you certainly write the last line down. And it's important you distinguish between the two of them. So you do say y equals this, dy dx equals this. Don't just have all these equals going there and hope someone works out what you're talking about. But also match the notation that's being used. So if they give me the question y equals x squared plus 2x, then I give the answer dy dx equals 2x plus 2. Of course, another way I could do it, if y is x squared plus 2x, I could have said y dash, that alternative notation. But if they had said function x equals x squared plus 2x, then I would say f dash x is equal to 2x plus 2. I match the notation that's being used. And of course, finally, if they did it this way, d dx of the actual function, then I'd just go, well, that equals 2x plus 2. So match the notation being used. So 9c and 9d, let's play around with some calculus without having to use first principles.